Let's go to the next speaker, Silke Krol from Bari. And Silke is bringing us good news again. Another nanoparticle, which, as you will tell, what does it do? Nothing.
Okay, so I think we have every piece of information which we actually need to understand why the particles I'm presenting seems to be a very good system, let's say, perhaps for future drug delivery, because as Janusz already mentioned, they are not inducing kappa. Thanks. You destroyed my complete concept. Okay, so I will present two types of nanoparticles. One is functionalized gold nanoparticles. The other will be albumin nanoparticles. The albumin nanoparticles were developed as part of the Cosmophos project. Panos is here, so you will see that there's nothing revealed. Actually, there are more and more chemotherapeutic drugs which are now approved, and as you already heard, if they are pegylated, it looks like that they are causing kappa effect. If it's due to complement activation or other factors like antibodies, is now becoming clearer and clearer. But however, the idea was, okay, we need perhaps a different concept, which is not basing on pegylation in order to avoid opsonization, but other concepts. So the main problem is that we are dealing with materials which are more or less the same size of biological entities. And in the first approach, we tried. No, also this you already have seen that Janusz did a study and revealed that most of the already approved drugs are actually showing kappa, mainly because they are pegylated. But basing on what I saw today from Moeen and from Janusz, I think there is perhaps something more behind that, and I will introduce these two particles which are completely different, both in size, in surface functionality, and in some of their properties, and perhaps we can learn something from these particles to how to design our particles in a way that they prevent kappa. So the first nanoparticles are the particles from Francesco. They are the surface functionalized nanoparticles with charged linear ligands and hydrophobic ligands, which are usually arranging in patches or stripes on the surface. And these particles have usually quite interesting properties. They can enter cells through the membrane without using endocytotic pathways, but they have also other properties. Okay, this wasn't there this morning. And these particles, let's say, usually didn't show any toxicity in cell experiments, so we were curious to see what happens if we are injecting them in pigs, if they, let's say, cause any kappa effect. And we injected the particles repeatedly, and as you could see, there was no kappa effect in all the experiments, even up to relatively high doses like 1 milligram per kilogram pig, while, as you could see, the pig model was reacting when we injected zymosan. And in that case, why? Why are these particles different from what you have seen before? Okay, first thing is they have no PEG on the surface. The other thing is that actually Francesco did studies how his particles are interacting with proteins, and this could be perhaps a potential indication how we have to design our particles in order to prevent protein corona on the surface. Protein corona can be an indicator for aggregation, and as we heard already today, aggregates can be recognized, can be uptaken by macrophages, and can cause kappa effects. So he found two things which are interesting. First, first he found that due to the surface structure, the human serum albumin, or in this case I think it was bovine serum albumin, is binding in a different way. So there is no denaturation of the proteins, and there is a very low binding affinity of the proteins to the particle surface. So it looks like that only a soft corona is binding and not a hard corona, which means that at the end, the particle size is not changing dramatically, and these particles have a very, very low level of aggregation, which is different for the other particles, for the charged particles. In this case, usually aggregation is more commonly observed, and in that case, most probably there will be kappa just due to the fact, even if everything else is similar, the size of these particles is usually very small, you will prevent that the striped particles will show kappa, while the fully charged particles most probably will show kappa, most probably just because one is less prone to aggregation and less prone to bind a protein corona, and for that reason they are quite stable, let's say, as single nanoparticles. The other point is that size in this matters. This is another study from Francesco in which he characterizes particles. In this case, it's not the striped nanoparticles, but just mousse. But he found that also in this case, the binding is less to smaller particles. So let's say a drug delivery with smaller particles will also prevent most probable kappa effects. But size is not the only thing which matters. As I said, small size seems to be an indicator to prevent kappa, but we did also experiments with urine serum albumin particles, and they were not small. They have usually 100 to 300 nanometer with, let's say, average diameter of something like 200. And they are not small. So will these particles cause kappa? They are very big, but they are natural material. It's human serum albumin, so it was not clear. We took the particles, we injected them, the first experiment, and as you could see, there's no kappa. Up to a concentration to 1 milligram. We were super happy about that result. We thought, wow, yes, great. And we try not only 1 order of magnitude of concentration range, but we try 2 orders of magnitude of concentration range. So we injected higher concentrated human serum albumin particles. And as you could see, we have strong kappa effect. What happened? We were really amazed because you see that even in this concentration of 1 milligram per milliliter, we see kappa effect, which was something we haven't seen before. You see that it's strongly concentration dependent. And the question was, why? What happened? And then we went back to the point when we did the preparation. In order to get, let's say, this preparation, usually what you are doing is you are preparing a stock solution. So we prepared a stock solution of 1 milligram for the first experiment and a stock solution of 10 milligram per milliliter for the second experiment. And what happened is that at that high concentration, the particles start to aggregate. They were also only for a very, very short period. They were stable, and then they were starting precipitating. And what we did in this experiment was we took the stock solution and we were diluting it for the 1 milligram per kilogram experiment, still having some of the aggregates in the solution which we were not able to completely solve. And that most probably was the explanation why we could see this concentration-dependent kappa. So be very, very careful about your conditions, and also, because the main problem when you're testing for kappa is that, let's say, you can only inject in bolus injection a certain amount. So if you want to go for very high particle concentration, because perhaps you have a very low drug loading, your problem is you will increase the amount. But it's not necessarily, our particles are super stable. They are stable for months at lower concentration, but not at 10 milligram per milliliter. So at that point, we saw at a certain point, even by eye, we didn't expect it, we didn't realize it in the beginning when we injected the first peak, that we saw that slowly the solution were becoming opaque. And so for that reason, be very, very sure about the let's say, aggregation behavior of your particles. Size seems, on the basis of these results, not really to matter, because we have either very small nanoparticles like the striped nanoparticles, which are only 5 nanometer, or we have 200 nanometer nanoparticles. But they didn't cause cancer if they are not aggregating to microparticles. So that's more or less it. I'm thanking for financial support from the Cosmophos project for this. And I thank you for your attention, and I'm waiting for questions.
Thank you, Silke. That's great. Questions, please? Okay. No.
What was interesting about your last comment is everybody's concerned about the health effects of nanoparticles, but what you were showing, actually the nanoparticles are the safe ones, and when they become microparticles, they're unsafe. Is that what you just showed?
Yeah.
And my other question was, if you're worried about aggregation, I wasn't sure what fluid they're in. Are they in deionized water or some electrolyte? Because that would affect aggregation as well.
Yes, actually, this was the particle was solved in I think in PBS.
Right.
But however, the main problem was we are starting with a powder, and it was like, let's say we had in the beginning really single nanoparticles, which very quickly, due to the high concentration, started not perhaps really to aggregate, but to agglomerate. Yeah. And due to the fact that we didn't sonicate them for a very long time before use, I think we still had a very quick aggregation because of the high concentration. And I think in at least for the kappa, not for the general toxicity, these particles are usually not toxic, yes. But at least for the kappa activation, aggregation seems to play a very important role. So microparticles in terms of kappa are usually worse.
Yeah, thank you.
Other questions? Well, I think Silke, thank you very much, and particularly many thanks for highlighting the fact that our model may enable to show aggregation and other physical chemical properties, their importance. And the next